Now we need to estimate the sum of a series when we have been able to use the integral test up till now to show that the series is a convergent. And if I'm given a series sigma an, and I can test for convergent, and I found that this series is a convergent series. And now further I need to find the sum of this series. Okay, to find the sum of this series is not an easy task. All I can do is find an approximation to this summation. If I could approximate the sum of S by any one of my partial A, by any one of my partial sums. Actually, for example, I could say that S is equal to S10. If I'm going to add up 10 terms of my series, and this will be an approximation to my series. One other one could say, no, I'll take further and I'll take 100 terms, and this will be my approximation, and so on and so on. If any one of this actually is an approximation to my sum, but how good is such an approximation? I don't know how good it is until I find an estimation of my remainder terms. But when I say I'll take 10 terms, actually this means that I summed up A1, A2, and so on up to A10, and I stopped, okay? And this actually is my approximation. What are the terms that I neglected here? Actually, I neglected the terms A11 and A12 and A up to A infinity. مش كده؟ يبقى I neglected all out these terms. I'll call the neglected terms my remainder terms. يبقى if I only took 10 terms, يبقى my remainder terms I'll call it RA, R10, and so on. Got the idea? يبقى in general, if S is approximated by Sn, يبقى my remainder term actually in general will be the terms that have been neglected, which will be the terms an plus 1, an plus 2, and so on, okay, up to infinity. يبقى the main idea now is how to find a bound for these error terms. We will use the same notation and ideas as we did in the integral test, assuming that f is decreasing on the interval from n to infinity. And I'm going to compare the areas of the rectangles with the area under the graph of f of x, as shown in this figure, for example. When I look at the remainder terms here, the remainder terms will form these rectangles under the graph, which are the first rectangle here is an plus 1, an plus 2. Actually the sum of these areas are my remainder terms, okay. طيب, what is the relation between these rectangles and the area under the graph from n for values of x greater than or equal n? Actually they are less. يبقى we'll arrive at this inequality that the remainder term is less than the area under the rectangle, the area under the graph of f of x from n to infinity. On the other hand, if I took the heights of the rectangles above the graph, like this case, and here, the remainder terms Rn that starts from n plus 1, n plus 2, and so on, is compared to the area under the graph for values of x greater than or equal n plus 1 this time, okay? And I noticed from figure that the area under the graph of f of x will be less than my remainder terms. If I will arrive at this other inequality that will give me a lower bound for my remainder term. If now I arrived at these lower and upper bounds for my remainder terms of when I take an approximation for my sum to be Sn, okay? If it is bounded below by the integral from n plus 1 to infinity of the function f of x dx, and it is bounded above by the integral from n to infinity of the function f of x dx. By using this previous argument, we have arrived to this to these error estimate rules, that my remainder term bounded above and below if and only if I'm dealing with a function which is a continuous positive decreasing functions for values of x greater than or equal n, and the series is convergent. If all these conditions applies, then I have my bounds for the remainder term. Also, I could bound the approximation, the sum نفسه, I can say that the sum is approximated by Sn, and in addition I could find bounds for Sn. if I added Sn for all these terms of the inequalities, I'll end up with the Rn plus Sn, which is my S in the middle. But my sum will be bounded by the partial sum plus these error bounds from above and below. Now let's do this example in estimating the sum of a series 1 over n cubed. First of all, we need to check that this series is a convergent series. It is a p series with p is equal to 3, where 3 is greater than 1. It is a convergent series. It is a p series convergent for values of p greater than 1. The second thing, he told me to approximate the sum with a partial sum of 10 terms. The sum will be approximated by this as 10. Approximating by S10 means that I'm going to add up the first 10 terms. 1 over 1 cubed plus 2, 1 over 2 cubed, 1 over 3 cubed, and so on, 1 over 10 to the power 3. Adding up using a calculator, simply I'll end up with this result, 1.1975. What is this value? This value is the approximation of my series. He told me to estimate the error involved in this approximation. I know that the error involved is the error involved in the remainder terms that I have neglected in this summation. My remainder terms actually are the R10. Okay, I neglected the term 11, 12, 13, and I call these remainder terms, as we have seen in the analysis, Rn. Okay, I know that Rn is bounded by the integral from n to infinity, and from 10 to infinity of the function f of x, where f of x is related to my function. The function related to 1 over n cubed is the function 1 over x cubed. If I'm gonna integrate the function 1 over x cubed dx, okay, the integral simply here is the integral x to the power -3. I'm gonna raise the power by 1 هتبقى x to the power -2 and divide by the highest power, substituting with the limits, and the infinity 1 over infinity will turn to 0, but then 1 over 2 times 10 to the power a squared. But the value of the remainder term actually is 1 over 200. But this summation actually is approximated by the value 1.1975, and at most there is an error of 0.005. بالتالي 1 over 200, which is 0.005. I know that my error R10 is bounded at most by this value. Okay. In the second part of the problem, it is requested to find how to improve the accuracy. In the first part, we found that the accuracy was 1 over 200, yani 0.005. That is, I need to improve my error bound. I need it to be better, yani smaller, yani 0.0005. Definitely, I need to add up more terms. But how many terms should I add? But that is what we want to find out. I could rewrite this problem or restate this problem as find n such that the error bounds is better. It is a 0.0005. Okay, and now I need to solve this inequality. I know that my error bound is bounded by the integral from n to infinity 1 over x cubed dx. I'm still dealing with the same function of series 1 over n cubed. But this is my related function. I need it to be less than 0.005. I need to solve this inequality. Integrating 1 over x cubed actually is -1 over 2x squared. Substituting by the limit at infinity, 1 over infinity is a 0, then I'll end up with the value 1 over 2n cubed, n squared, sorry. 1 over 2n squared must be less than 0.005, which is actually 1 over 2000, right? Let's simplify, do our cross product, then I'll end up with n squared greater than 1000. That is, n is greater than, taking square root both sides, 31 مثلا 0.6. I know that n must be positive. I'm adding up terms that don't take plus or minuses. Also, I know that I want it to be greater to achieve this accuracy. So it must be an integer. I'll take the next positive integer. The number of terms to ensure accuracy within 0.005 actually is 32 terms. يبقى my S to have better accuracy I must take my partial sum S of 32. Okay. Just a final remark that we must note that the integral test only states that the series is convergent or divergent, but it does not give any clue about its summation. To find the sum of the series, all we can do is find an approximation to the infinite sum with a partial sum. Any partial sum Sn will do, but how good this approximation will be, actually we will use our estimates of a estimate